Hey teachers, welcome back to section 2-3 part 2. We're talking about other set operations and their properties. If you'll recall, we've talked about intersection and union. Intersection are the elements that are common to both sets, and a union is where you combine two sets together. So we left the last video with this problem, example 19 part D, and I encouraged you to find a set representation for the shaded region here. Hopefully you've had a chance to work on it. If you haven't, go ahead and pause the video and see what you can do with this. Now keep in mind, our answers are not unique. You may do it a different way than I do it. I'm going to do an answer and then I'm going to show you the ways the book has it listed. When I see this, y'all, what I think about is this is set A combined with set C, but it's got too much going on, right? It's got extra, well, not too much, I'm sorry, too little. We've removed some stuff. So how about we do this? Let's do, and this is just the way I'm thinking, A union C. Now, highlighter, A union C would be this. Right? But that's too much. So I'm going to use the difference of sets and I'm going to subtract out, and remember I'm using that, I really shouldn't be saying I'm using a difference of sets, and remove a intersection B, which is what? Is this part right here. And I'm going to remove, think about this B intersection C, that's this part right here. But notice I removed too much, so I'm going to combine that with, this is getting too big, this very middle part. I'm going to highlight this a different color. I've got to add back this part right here, right? If I add that back in, that would be union. When you add something back in, it's a union. Then it would be A intersection B intersection C. Now that is certainly can't be the most simple version of this. Okay, and again, let me erase, and that gives us that set right there. So A union C, that's all of A combined with all of C, and I'm using the difference of A intersection B, which is this part right here. So that part comes out, and B intersection C comes out. And so what that does, unfortunately, is it gets rid of that green part in the middle that we want. So I union that back in, A intersection B intersection C. Now I'm going to look at their result or results and compare. They easily have this far more simplified than what I have. All right, so let's talk about it. The first one's A union C, and they difference B out. So A union C, and they get rid of all of B. Okay. Unioned A intersection B intersection C. That's kind of like what I did. But that doesn't get rid of... Oh, it does get rid... Look, that gets rid of all of that. That was easier than what I did for sure. Very similar, but easier. So again, A union C. This is A union C. And then they differenced B. So what that did is it got rid of, it got rid of that. Okay. That is a lot simpler than what I did. But then they unioned this back in, which is A intersection B intersection C. Then they have another option. Let's take a look at that. Okay. Going to erase. I'm just kind of scribbling, thinking through this. So here we have the set A, the whole set A, and they're doing the difference of B union C. Okay, so the whole set A, and then they're getting rid of this part. You combined with the whole set C, and they're getting rid of this part, and then their union A intersection C. Yes, and that would add that back in. But you might want to spend a little bit of extra time just pausing the video and taking a look at those on your own. It takes some thinking through. And again, notice they're not unique. My answer was probably not quite as streamlined as either of these, but it's the same idea. All right, so example 20. Suppose M is the set of all students taking mathematics and E is the set of all students taking English. Okay, so notice we have a Venn diagram. This would likely be considered students. We have a circle here to represent mathematics. That's the M, and another circle here to represent E. Identify students described by each region in the figure. So we want to look at this just one at a time. So let's take a look at region A. I'm going to highlight it for you. Region A is considered this moon-shaped piece, crescent, that we have right over here. Okay. Notice those are values in M, but not in E. What does that really mean? Well, if we put that in words, that could be students that take mathematics, but not English. Let's see the way they have typed. Region A contains all students taking mathematics, but not English. And you could write it as the difference in sets M and E. All right, now, time for you to pause the video and describe sets B and C separately. The next one I'm going to do is B. So if we were to describe in words what set B is, notice that's this leaf-shaped piece in the middle. That is the intersection of set E and set M. So those are elements that are both in E and M. E represents English, M represents mathematics, so surely that's students that take both English and mathematics. And there it is, region B contains all students taking both mathematics and English, or M intersection E. All right, now how did you describe C? So C is the crescent-shaped piece on the right. C are elements that are included in E, but not included in M. The notation for that would be the difference of E and M. E with that minus symbol and then an M. And those are students that take English but not math, right? And they described that as students that take English but not math. Okay, now we want to describe D. You see the D down there at the bottom? So those are still students, but they don't take math and they don't take English. So they're neither taking math nor English. How could you describe that in set form? I can't get my slide to change. There we go. Okay, so region D contains all students taking neither mathematics nor English. That's what we said, right? Now check out this way of expressing it. So you could say it's the complement of M union E. Now remember, M union E is anything in a circle period, and the complement would be anything outside of that. That would be the way that I would think about it. Or you could take M complement intersection E complement. In other words, what does outside of M have in common with outside of E? And that will give you anything, again, that's not in a circle. All right, next example, example 21. Here's a good one. In a survey that investigated the high school backgrounds of 110 college freshmen, the following information was gathered. 25 took physics, 48 took mathematics, 10 took physics and mathematics, 8 took biology. You can read all this, right? So we got a lot going on here. So we want to answer a few questions about this. Before we address this, let's look at the questions. Okay, so we have students that took physics, mathematics, physics and mathematics, biology and mathematics, physics and biology, all three, and biology, all listed separately. They want to know how many students took biology but neither physics nor mathematics, how many took physics, biology, or mathematics, how many did not take any of the three subjects. And to solve this problem, we do need to build a model using sets. We need a Venn diagram. And so I have one for you that I've doctored up just a little bit. We're going to work on this together. Okay. Now, notice what's going on. Ignore the green in the middle. Okay. So notice there is a circle representing physics, there's a circle representing biology, and a circle representing mathematics. Now, back to the green in the middle, the 5. What in the world is that? I've already gotten started on filling in the diagram. Let's go back to our list of information. Notice, if I highlight, it says 5 people took all 3 subjects. If you know information about how many fit in the intersection or in the center, if you have 3 different sets represented, start in the center. So that's what that 5 that I put in right there represents. So now what I think I'm going to do is I'm going to take a look at this part right here. Okay. Now, what does that part represent? Well, that part right there are students that took physics and mathematics. The P and the M, right? So if I go back and look at my list, how many, we need to find it, took both physics and mathematics? I see it right here. Okay, so notice I'm not doing these in order. I'm finding intersections. So 10 students took physics and mathematics. So I go back to my list. And do I put 10 right here? Well, no. I've already included 5 students that took all 3. So 10 students total took physics and mathematics. It didn't say 10 took only physics and mathematics. So that means there are 5 students that took only physics and mathematics. But now I have 10 in my leaf for physics and mathematics. You follow how I'm rolling with this? So next what I want to do is I want to take a look at maybe this one. Now what does that leaf represent that I'm trying to highlight in aqua here? Well, that's physics and biology. So let's go back and look at our list for physics and biology. There it is. So 6 students took physics and biology. So let's go back and put 6. Do I put 6 in there? Well, no, right? I've already got 5 included in the aqua highlighted. So I need 1 student took only physics and biology. 5 of them took all 3. All right, so I'm working my way out. So always start in the center. Next, let's use yellow. Let's take a look at this intersection area. Now that intersection area you'll see is biology and math. So let's go back and look at my list. And I'm looking for biology and mathematics. And there it is. Although my pen's not working. Y'all, I apologize. Each time I change a slide, I have to click my pen. I know that's a lot of clicking. And then sometimes it just doesn't do right. So 8 students. Now, do I put an 8 out there? No, I do not, right? I've already included 5, and that leaves 3 out here. Now I get to work with the outside circles. So let's look, I'm not going to highlight anymore. Let's look at the P, physics. How many students took physics only? Or just physics, okay, or physics. It's not physics only. Let me make that clear. Took physics, period, 25. So I go back and I look, and that whole physics circle needs to include 25. Well, what I need to do then is I need to do, for that number, I need to do 25 minus the 5 that I have here, minus the 5 that I have here, and then minus the 1 that I have there. All those are in the physics circle. So that's going to be 14 that goes here. Follow how I'm rolling with this? All right, so biology. What color do you want biology to be? How about pink? Okay, so how many students took biology? 45. So I go back to my circle, and my biology circle, I have 45 total, but I can't put that out here because I've already included 1 student up here, 5 students in the center, and then 3 students that took biology and mathematics. So that's going to be 45, 44, 39, 36. Hopefully I did that subtraction right. Let's add it back to be sure. 3 plus 5 is 8 plus 1, 9. No, 36 plus 3 is 39, 44, 45. Yes. I can't check my work. And then finally math. How many students took mathematics? Looks like 48 took mathematics. So when I fill in my mathematics circle right here. Oh, well, look there. Why did that pop in there? Is it 35? Let's find out. My pen wasn't working and things magically appeared and they weren't supposed to. Let's see if that's right. And then some weird stuff erased. Don't ask me how that happened. I don't know. So how many was it? 48 took mathematics. Okay, so I have 48, but in my mathematics circle, I already have 5 and another 5 in the center and then another 3 over here in the biology area. So 48 minus 10 is 38 minus 3 is magically, look, it was 35, so it's right. And then how many students do we have altogether? Notice back up here at the top, we have 110 students, period. So how could we figure out what goes on the outside? Is it possible that students didn't take anything? Well, no, they didn't take physics or biology or math. Are there any other classes other than physics, biology, or math? Of course there are, right? So I need to do 110 minus all of these numbers, right? So minus 14, minus 36, minus 35, minus 5, minus 1, minus 3, minus 5. So I'm going to subtract every number that's in that circle. My advice is to do that in some organized manner. So pick the outside ones. Minus 14 is on the outside. Minus 36 is on the outside. Minus 35. Then go to those leaves. Minus 5, minus 1, minus 3. And minus 5. So I have 11 students. I didn't write down all of that, but all. Okay. That gives me 11 students that are not taking physics or biology or math. They're not taking any of those courses. Okay. Now we can answer questions using our picture. So let's go back to the questions. How many students took biology but neither physics nor mathematics? Okay, so look, 36 students took biology but not physics because that's in the physics circle, and not mathematics because that's in the mathematics circle. So the answer to that question is 36. How many took physics, biology, or mathematics? Now what is that asking? They took physics, biology, or mathematics. That's any of those. As a matter of fact, if we add all those together, that's the all number that I have here. So that's going to be, is that 99? It is, right? I was just working backwards there. But if you add all those numbers together, that would give you 99. Okay. How many did not take any of the 3 subjects? Remember, that's 11. That's what we found out last. Okay. And of course, to solve this problem, we build a model. We sure did. And we filled it all in. Aren't those great problems? I think you'll enjoy those. Next, I want to define Cartesian products. One way to produce a set from 2 sets is by forming pairs of elements of one set with the elements of another set in a specific way. Suppose a person has 3 pairs of pants. So you have blue and green and white pants, and then 2 shirts, blue and red. How could you combine those every way possible to get outfits? Well, if you started thinking about it, right, you could put the blue pants with the blue shirt. You could put the blue pants with the red shirt. You could put the green pants with the blue shirt. I can start drawing arrows here. So blue pants with the blue shirt, blue pants with the red shirt. We could do green pants with the blue shirt, green pants with the red shirt. PowerPoint's getting mad at me. And then finally, we could do white pants with the blue shirt, white pants with the red shirt. Now, if you followed all of those arrows, you would get 6. Is that the way to organize it? Maybe not. It says, according to the fundamental counting principle, you remember that? That's when you multiply, right? The fundamental counting principle. There are 3 times 2, 6 possible ways to pair an element from set P with an element from set S. P, remember, is the pants. S is the shirts. There were 3 options for pants. There were 2 options for shirts. Fundamental counting principle, 3 times 2 is 6 options. All right, we've done that before. Here's a way to organize it. I think I like my lines better, but whatever. So blue, blue, white, blue, green, blue. Remember, the first one is the pants listed. The second one is the shirt. Then you can combine blue with the red. So blue pants, red shirt, white pants, red shirt, green pants, red shirt. There's all 6 of our option. Because the first component in each pair represents pants, and the second component in each pair represents shirts, the order in which the components are written is important. It's definitely important. That brings us to a definition. Equality for ordered pairs. Okay, XY is equal to MN. Now, you might recognize this notation when you plot points in a rectangular coordinate system. Those are ordered pairs also. You don't have to be just talking about a rectangular coordinate system, but those are definitely ordered pairs. But this goes on to say, if and only if, remember that's a biconditional, you read that both directions, the first components are equal and the second components are equal. In other words, X and M have to match and Y and N have to match. Now, what I want to point out here, this is very important. The ordered pair 2, 3 is definitely not the same as the ordered pair 3, 2. That may seem obvious, but I want you to realize those are not the same thing. A set consisting of ordered pairs is an example of a Cartesian product. And that's why you hear the XY axis or the rectangular coordinate system often called the Cartesian coordinate system. So you know what I'm talking about, an XY axis, where you plot points. And we could plot the point 2, 3, which would be right here, and the point 3, 2, which is right here. Clearly, they're not the same. But you do not have to represent this in terms of a Cartesian coordinate system like this. It doesn't necessarily have anything to do with graphing. You don't even have to have numbers as your ordered pairs. This could relate to pants, right? Which was colors and shirts. For any sets A and B, the Cartesian product of A and B is written as A cross B. Now, I know that looks like an old school multiplication symbol, but that is red cross, is the set of all ordered pairs such the first component of each pair is an element of the first set, A, and the second component of each pair is an element of the second set, B. Notice the set builder notation. By now you're kind of used to it. Notice it says parentheses. So if you ever see parentheses, this is an ordered pair. Careful. This and this is 2 different things. Okay, so again, this is an ordered pair. This is what we're talking about right now, where these curly brackets are just a set. The order in a set doesn't matter. The ordered in an ordered pair absolutely does. And it says X is from the set A and Y is an element of the set B, 2 different sets. It says, note that A cross B is commonly read as A cross B. It should never be read as A times B. It is not A times B, not even close to A times B. Okay, hang tight. We're almost done with section 2-3. We just want to do a little bit of cross product examples. So it gives us the set A Notice the elements are A, B, C. The set B are the elements 1, 2, 3. We are asked to find A cross B. Okay, so you're actually listing the Cartesian product. So remember what you do. You let A be paired up with 1. So that's going to be A1. Then you can let A pair up with 2. So A2. Then you let A pair up with 3. So A3. I need to write smaller. Then B pairs up with 1. So B1. B with 2. That's B2. B with 3. So that's B3. I'm not finished. Then C can pair it up with 1. C with 2. And then C with 3. Does that make sense? Okay. There is no 1A. Because A is first, B is second. No other way to do it. Notice how many elements are in the set A cross B. And by the way, if I write that as a set, I still need my little, and really writing it horizontally would be better with commas between all these guys. I try to do the next one B like that. That would make more sense, wouldn't it? I'm not even going to re-video it. I'm just going to keep it just like this. So B, let's do this in a method that we should. So it is a set. This is a set of values. B cross A. So B comes first. Hey, stand by, look. I got it typed up for you. So notice A cross B. I have my curly braces here to represent a set. I have commas between all the elements in the set. And the elements in the set are ordered pairs. It's a Cartesian product. So there's the what we have listed, A1, A2, A3, A4, B1, B2, B3, and C1, C2, C3. And so on B, question B, I need B cross A. I need my little curly brackets to denote a set. Now B comes first. So that means I need to put 1 with A. So 1 from B, A from A. And then I'm going to put 1 with B. And then I'm going to put 1 with C. Then what am I going to do? I'm going to move on to 2. So 2 goes with A, 2 goes with B, 2 goes with C. 2A, 2B. Make sure you put commas between these, comma 2C. And then finally, 3 goes with each of those. So 3A, 3B, 3C, and I close out curly braces to close out my set. So that's B cross A. Are A cross B and B cross A the same? Absolutely not. The order of a Cartesian product matters a lot. There is no commutative property there. What about A cross A? What in the world? And let me show you the typed version of this too. I think you'll appreciate seeing it typed. There it is, just like we did it handwritten. All right, so look, A cross A. Let me back up. You don't want to see A cross A yet. Ha, took it away. All right, so question C. Take your time, pause it, do A cross A. So A cross A. Curly braces, right? Proper notation, very important. So I'm saying A with A. So A with A. So that's A, and then A goes with B, and then A goes with C. All right? Let's move on to B. B goes with A, B goes with B, and B goes with C. And next we got C goes with A, C goes with B, C goes with C, and close out those curly braces. Now, typed up version, there you go. Looks good, doesn't it? Now, one thing I want to point out, remember the fundamental counting principle means we can multiply these together to figure out how many you're going to have. What am I trying to say here? So A has 3 elements, B has 3 elements, so there should be 9 ordered pairs. Count them. 1, 2, 3, 4, 5, 6, 7, 8, 9. Sure enough, right? And the other way around, B cross A. B has 3 elements times A has 3 elements, also 9. And even A cross A, 3 times 3, fundamental counting principle equals 9. All right, for our last slide, it is possible to form a Cartesian product involving the null or empty set. This is a little strange, y'all. Suppose A is the set 1, 2. Because there are no elements in the empty set, there are no ordered pairs x, y with x as an element in A, because you could use 1, but what are you going to pair it with in the empty set? Nothing. So it turns out if you do a cross product with the empty set, notice right here, and it wouldn't matter if you did A cross the empty set or the empty set cross A, you get the empty set. So it's not impossible to do, but it sort of is. You get the empty set. So, hey, look, it's right at 30 minutes and I finished this section. So you don't have to come back for a part 3. Matter of fact, this wraps up module 1, at least the way things are right now. So I hope you have a wonderful day. Please reach out if you have questions and take care.